The analysis of the physics of a simple pore begins with the observation of water exiting a small hole in a bottle, a phenomenon driven primarily by gravity. This setup reveals several distinct fluid behaviors, including a continuous jet that starts horizontally before curving into a parabolic trajectory. The flow is characterized as laminar and smooth near the opening, and the flow rate is observed to decrease as the water level or pressure head Hertz drops. To mathematically describe these forces, we rely on the Navier-Stokes equations for incompressible flow, which balance inertia, pressure gradients, viscosity, and gravity. Because the complete equation is notoriously difficult to solve, the analytical approach requires making several justified physical assumptions to simplify the model. These include treating the water as an incompressible Newtonian fluid with constant density and viscosity. Furthermore, the system is analyzed as a quasi-steady flow where air resistance is negligible and the pressure at both the water's free surface and the jet outlet is equal to atmospheric pressure. By simplifying the equation, it becomes clear that the flow is primarily a balance between inertia, the pressure gradient, and gravity. This theoretical framework directly explains moves downward in a clear arc. This happens because of the gravitational term ρ in our fluid equations. Gravity is constantly accelerating the fluid toward the ground, which transforms a straight horizontal exit into a classic parabolic trajectory. Moving on to the quality of the stream, we observe that the jet remains smooth, or what we call laminar flow. This is a result of the physics of scale. Because the water is exiting at a relatively low velocity through a small opening, the viscous forces dominate over the inertial forces. Essentially, the thickness or internal friction of the water is strong enough to keep the particles moving in orderly layers, which prevents the chaotic swirling of turbulence. Finally, we observe that the flow rate decreases over time, with the stream getting weaker as the container empties. This is directly tied to the pressure gradient term delta. The driving pressure behind the water is proportional to the height heat of the water level above the opening. As that height drops, the pressure drops along with it, which naturally reduces both the exit velocity and the overall flow rate. This confirms that our physical model accurately predicts the real-world behavior of the fluid. Modeling and simplification is a universal principle used across various fields, including aerodynamic design, civil engineering, and meteorology.